We'll start with the third lecture of Benjamin Huard.
Thank you. Okay, thanks a lot. So this will be the last lecture of the series, and so I'd like to start with by continuing on part 2. So to remind you, we've already looked at part 1. So why are superconducting circuits a good platform for probing quantum trajectories? We've started discussing the modeling of what's let's say the input-output theory. So how signals propagate in transmission lines, and how homodyne, heterodyne measurement and photodetectors work. And then I stopped for a bit here and jumped to these first 3 points. But now I'd like to come back and discuss quantum amplifiers, quantum limited amplifiers. So these are essential tools actually, and so there have been so the amplifiers are absolutely necessary if we want to see quantum trajectories, because if we don't use quantum limited amplifiers, it's impossible to not be totally blurred by the technical noise coming from all the measurement line, and so it's been a topic of interest. I mean, the first microwave amplifiers were quantum limited microwave amplifiers were looked at in the 80s by Huard, but it's a field that has been revived, let's say 20 years ago, precisely for this application of trying to reach the quantum limits in superconducting circuits. And so I'm going to discuss a bit what they are. So I showed this slide already. So there are various kinds of amplifiers that are based on superconducting circuits. Ones that are degenerate, so a single mode is used to amplify the signal, or non-degenerate amplifier, where there are two specially delocalized modes that play the role of a signal and the idler. We'll discuss what that is. And more recently, the field has embarked into this new kind of amplifiers, which are called traveling wave amplifiers. So essentially, it's a nonlinear line in which we send a pump tone. The signal and the idler are also traveling as well. And so one challenge is to have a good phase matching condition along the way. But this provides a really wide band amplification. So it's a very convenient tool now. And a topic of interest these days is the possibility to make these amplifiers non-reciprocal, in the sense that you want the signal to be amplified towards the detection setup, so the analog to digital converter in the end, but you don't want the signal to be amplified and partially reflected back to the quantum system, because it would dephase the quantum system or introduce unitary or decoherence evolutions to the system. Okay, so I'm going to maybe go to the blackboard to discuss this. So all right, so last time I'd like to point two main points, two main conclusions that we arrived at last time. So for homodyne detection. So again, homodyne detection is what happens when you demodulate the signal at the frequency you demodulate at the frequency of the signal. And in this case, the probability to find a given quadrature value x is given by the marginal of the Wigner function directly. In the case of heterodyne measurement instead, so heterodyne is when the signal with which you demodulate is non-resonant with the signal of interest. In this case, the measurement contains two components. So first, the signal is now a complex number, so it's made of two real numbers, which are the two quadratures of the signal, where it's polluted by a new mode, which we may call the idler directly. But so this extra mode, which lives in the spectrum at the mirror frequency compared to the measurement frequency. So this mode is optimally empty. So we'd want we could do even better if we were to squeeze it in the right quadrature actually. But we let's say it's empty at best for now. And so this extra mode will pollute your signal. And as a consequence, we see that the probability distribution to find quadratures x and y, so which are right as a complex number again, are directly given by the Q function, the UZMI Q function, and not the Wigner function anymore. And the relation between the Q function and the Wigner functions are that they are the Q function is the Wigner function convoluted by some blurred function, which is the Wigner function of the vacuum. And this Wigner function of the vacuum directly comes from the noise of this extra mode we are polluting the signal with. Okay, so with this, I'd like to now describe these quantum limited amplifiers, and you'll see you'll see the rows of these Wigner and Q functions in the amplifier. So quantum limited amplifier. Okay. All right. So what's the role of the amplifier in a quantum measurement experiment? So the role of the amplifier is to increase the overall signal to noise ratio. So it's to increase the overall signal to noise ratio, but we will see that this is a bit counterintuitive at first because there's a powerful theorem which says the cave theorem, which says that an amplifier must add noise. So you would think that in fact this is a bit counterintuitive. What I mean by overall signal to noise ratio is that in the end, the signals we want to send, we want to measure, they will arrive at the final detection apparatus, which is again this analog to digital converter in our case. And this equipment is noisy. So this equipment it sits at 300 Kelvin. At 300 Kelvin, microwaves have so the microwave modes have a lot of thermal excitations. And actually, 300 Kelvin would be even a pretty good temperature, but actually there's a lot of added noise by this object itself. And so if you want the fact that we want that this ADC adds a lot of noise compared to the vacuum fluctuations. To vacuum fluctuations. So this is what we have to struggle against. So essentially, these amplifiers we're going to build, their role is to amplify sufficiently well the vacuum fluctuations that we want to preserve, which are really part of the quantum signals we want to measure. We want to amplify them high enough in order to completely overwhelm this finite noise that's unfortunately a bit unavoidable. Okay, so maybe first to model what happens at the level of this ADC. So we can directly write the probability distribution to find a complex amplitude. So the sum of the two. The complex sum of these two quadratures. So this probability distribution to find a given number alpha is again the Q function of what's coming inside of the ADC, so the mode of interest, but it's convoluted by the UZMI Q function of the thermal Gibbs state at a temperature T. So so here we write the thermal state. So it's a diagonal state, right? Diagonal density matrix, which you can write like this. So it's so this Q function will be you see it's not the Q function of the vacuum. It's not the same width, but it's also a Gaussian distribution in 2D. and it's simply enlarged by the temperature. Okay, so if we want to be more quantitative, so this as a function of temperature, this Q function at a temperature T, we can write it conveniently with the Boltzmann factor. So I introduce nu equal to the Boltzmann factor minus h bar omega over kBt. So the Q function is this normalization this prefactor 1 minus nu over pi times exponential of nu minus 1 alpha squared. Okay, so you see that at large temperatures, indeed, this prefactor in the exponent gets smaller, which means that the variance gets larger. Okay, so to give figures, right? So if we consider a temperature of the room temperature of 300 Kelvin and 5 gigahertz, which is a typical signal frequency, you can compute easily that the variance of Qt is about 10 to the 3. So times the variance of the vacuum of the UZIMU function of the vacuum noise. So you see, it's there's really 3 orders of magnitude to fight against if you want to overcome this noise. So we really need to amplify and do it properly. Okay. So now let's consider how an amplifier works. So what do we want to do? So we would want an apparatus which is symbolized like this, right, with a gain on the energy G. So we would put in incoming modes A in and outgoing modes A out, and so the goal of this amplifier, at least for now, we'll consider what's called phase-preserving amplifier. So amplification that does not depend on the phase of the signal. So in this case, we want that the average value of the outgoing amplitude, so the outgoing, the complex amplitude of the outgoing wave, is a square root of G times the incoming amplitude on average. So this is the target. And so something that seems a bit simple is to say, okay, so maybe the relation I want to build an equipment which verifies this relation at the level of the operators themselves. So is it possible? And we can quickly see that in fact this is not possible to have a unitary operation that verifies this simple relation. And the reason is that we need to preserve the commutation relation. So if I write the commutator A in dagger A in, so here I work in this with these modes that have some temporal envelope, right? So the commutator is 1 and not delta of t minus t prime or omega minus omega prime. So the commutator is 1. But I also want that the outgoing mode operator verifies the same relation, right? So we also want that the outgoing mode commutator is 1. But this one, if we manage to make a device which works with this relation, this one would write G times A in dagger A in commutator, which is G. So you see directly that the only solution for this is that G is equal to 1. So the only way to verify this simple solution to our problem is to have an amplifier that does not amplify at all. Right? So this is not a good way to do it. So there are 2 ways to fix it. I mean, there are more ways, I guess, but 2 simple ways to fix it. One way is to it's what's called the phase. So it's our part 251. It's what's called the phase-preserving amplifier. Okay. So one way to restore a proper commutation relation is to introduce an extra mode. So not unlike what we have seen for heterodyne measurement, actually. So we would indeed have embryon of the relation we want to have, but we need to add another term, which on average would be 0. So on average, our relation of amplification would still be valid. But this time we add an extra mode, which I call B in dagger. So this mode A would be in the amplifier language. This mode A is the signal, and this mode B that we introduce now is called an idler. And you can check quite easily that if we owing to this dagger here in the relation in this input-output relation, owing to this dagger, if I compute the commutation relation of A out dagger and A out, I get 1. So this time this is fine. This new relation indeed repaired the problem. So indeed A out dagger A out is 1. So this is okay. And so if we want to still have this amplification, phase preserving amplification on average, the only constraint is that we need the mode B in to be of zero average value. So if B in is 0 on average, which is the case, for instance, the case of a thermal state, right? So if B is in a thermal state, then you see that indeed on average, A in is equal to square root of G A out is equal on average to square root of G A in. So we can do this. Okay. So now comes the question of what unitary operation do we need in order to make this to have this operation between A out and A in and B in. So in fact it's a quite simple unitary operation. So the unitary operation that corresponds to that is called the two-mode squeezing operator. So the unitary is actually it's called S of R. There's a parameter R which will tune the gain. Actually, the link between the gain and R is that the gain is cosh R squared, and S of R is defined as an exponential of 1/2 of R star A B minus R A dagger B dagger. So this is a two-mode squeezing operation. So you see that if you look at what's in the exponential, so this is what the Hamiltonian term would look like. So we need a Hamiltonian which has a coupling term between modes A and B, which is like this, right? So A B plus A dagger B dagger. So one way to do it is to use a three-wave mode mixing, for instance, where R would be proportional to some pump amplitude. So this is typically obtained in optics. It's typically obtained with a Chi2 crystal, a nonlinear crystal. So, and in the microwave domain, we can make it work with Josephson junctions, for instance, or disordered superconductors. Okay, so how do we see that we verify this input-output relation? Well, we can. One way to do it is to compute how the A operator, let's say A in operator, evolves with this under this unitary evolution, and you see that indeed what we get is cosh R A in minus sinh module of R exponential I arg of R. So there will be a phase knob if we change R times B dagger. Okay. So indeed, you see that if So cosh R square is the gain, and we indeed find the input-output relation we wanted. Okay. So now our question is what are the implications of this mode, this extra mode B in the idler mode on the minimal noise that we need to add for amplification? Is there a minimal noise actually? So you see that if I compute the variance of the quadrature X, let's say, X out, I remind you maybe that that a mode A, let's say A out, is X out plus I P out in this language, where X is A out plus A out dagger over 2, and P out is A out minus A out dagger over 2I. So these are the Hermitian and anti-Hermitian parts of A out. So beware in the literature there are 3 different conventions. So some use a square root of 2 here, some use 1 below. I prefer to have a real part and imaginary part. I feel it's better. Okay, so if you compute the variance of X out with this relation, you see that it's G times the variance of what was sent in on A in. So the variance of X A in plus G minus 1 times the variance of the X quadrature of B in. Okay, it's the same for P. Huh? We would have the same relation for the P quadrature. But now you see that if we compute the sum of delta, so what's the minimal noise that is added by this extra term, this unwanted term, the pollution coming from the signal, the idler mode. So if we compute delta X B in squared, so the variance of X for the mode B, plus the variance of P for the mode B, well, this so you know that the sum of the 2 squared is at least equal to 2 times the square root of the product of the 2 variances. So we can write this, and now we can use the Heisenberg uncertainty principle and show that this is with the conventions of the divided by 2 here in the quadratures. We see that this is larger than 1/2. So indeed, there is a minimal amount of noise that needs to be added to our signal. The output signal is indeed polluted by a minimal amount, and this is what's called the cave theorem for the quantum limit of amplification. Okay, so to sum up this expression, so what we're saying is that if we add the variances at the output, so of X and P, I divide by G to refer the output noise to the input level of the amplifier. So dividing by G, we renormalize the output signal to what was inputted. You see that this is at least larger than the incoming noise. So this one is unavoidable. We are willing to. We wouldn't want to degrade the incoming noise, especially if it contains information. But on top of that, we have this extra term, which is G minus 1 over G times 1/2. So sometimes this is called half a photon of noise that needs to be added in the process of phase-preserving amplification. Okay. So now there's something I find very interesting, which was found by Cave. So So let's, the question I'd like to ask is how do we deform the signal at the level of the probability distribution of finding some signal, right? So if I go back again, remember that if I do a heterodyne measurement, the probability distribution of the quadratures I measured is directly given by the Q function, the UZMI Q function. So the natural question is how does this extra mode, this idler mode, pollute the Q function of the signal that is incoming? So what we're going to do now is compute what's the Q function at the output as a function of the Q function at the input. And we're going to do it in a very similar way as what we have done before. So we are going to compute the moments of the outgoing mode, right? So if we compute so question is what is Q out as a function of Q in? So we're going to compute the moments for that. So the moments A out to the power M, A out dagger to the power N. And so if we want to compute that, well, we can replace these operators with the input-output relation. So it's a square root of G, A in, plus square root of G, minus 1, B in dagger to the power M, times square root of G, A in dagger, plus square root of G minus 1, B in to the power N. Okay? So like last time, like 2 days ago, we're going to say that we're going to assume that the mode B is in the most favorable most favorable condition to not pollute too much the signal we're inputting. So we assume B in is in the vacuum state. Okay, so that it adds the least amount of noise. But in this case, the calculation is quite simple again, because each time in this expansion, each time we will have a B in on the right, this term will vanish because of the B in times the vacuum is 0. And each time we will have a B in dagger on the left, we will again have some vanishing function because the bra 0 times B in dagger is also 0. So the only term that will remain again are the terms where there are no B-ins at all. So if I compute this, you see that the only term that remain are G to the power M plus N over 2 times A in to the power to the power M times A in to the power dagger to the power N. Okay. So essentially the moments in this order, the anti-normal ordering, and this is important because remember that the Q function, the moments of the Q functions are the moments written in the anti-normal ordering way, whereas the moments of the Wigner functions are the moments written in a symmetrically ordered way. So here we use read. So this will provide the statistics of the Q function, and what we find is that the only deformation in the moments between input and output, despite the fact that we have this pollution by the adler, is a global factor, which is the gain times the order of the moment. And so because of that, what we've just shown is that the Q function of the outgoing mode of this amplifier is simply given by a gain, up to a gain. It's simply given by the Q function of the input mode dilated by this gain. So maybe I can do a drawing. So to sum up what we found, so if I write real part of alpha, imaginary part of alpha, let's consider a mode that has some. So I'm going to draw to draw a Q function. Let's say here. Can you see something? Or, yeah. Well, it's not very clear. Sorry. Okay, maybe I'll just do it like this. Okay, so let's say this is the Q function of the mode. I just plot the contour, right? Let's. I don't want to be more complex than that. So this would be the Q function of what's coming in. If I want to know, by the way, what's the Wigner function of what's coming in, well, it's just the Wigner function is just a bit smaller in variance, because again the Q function is the Wigner blurred by the vacuum, the Wigner function of the vacuum, which is a Gaussian. So this would be the Q function, and then we want to know what's the Q function of the signal coming out. Well, what you need to do is a simple dilatation. So the Q function of the signal coming out will be simply exactly the same Q function as what's the input, but dilated. So that tells us that since the Q function is in one-to-one correspondence with the quantum state, you see that on paper we didn't lose any information in the output compared to what was at the input. So it's not. So I think it's important to know that despite the fact that indeed on the quadratures the variance gets larger by half a photon, the information contained of this outgoing mode is absolutely preserved. Okay, so in terms of computing the efficiency of the detection setup, if we want to do a heterodyne measurement, there's no added cost of using this kind of amplifier if the idler is in the vacuum. Okay. So this is true if we want if there is information in both quadratures, right? If we encode information in the two quadratures, because that's when we measure the two quadratures, we actually need the Q function, as we saw for heterodyne measurement. But instead, if all the information we're interested in is encoded in one quadrature, then we're going to lose, right? So here we're going to lose half the information by using this kind of amplifier. And so if we want to measure a single quadrature, yes. Ah, yes, very good. Yes, so indeed, in case, so there are indeed two solutions if you don't want to pollute a single quadrature you're interested in. So either indeed you prepare the idler mode in a squeeze state, as you say, a squeeze vacuum state, and if you infinitely squeeze it, indeed you would preserve the information. But the other solution, which is simpler, is to use a different kind of amplifier, which I'm going to talk about now. So these are called the phase-sensitive amplifiers. So this it's the kind of amplifier that Cater discussed in his talk, and it's also the one I showed last time for the measurement of sigma z and x and y at the same time. Okay, so how to build a phase-sensitive amplifier? So I remind you that we say that we could not have this relation here, but if we're interested in a single quadrature, we could start from this repaired version that is the phase-preserving amplifier input-output relation, and what we can do instead is replace the mode B in this idler mode. We actually replace it with a mode A in. So you see it's a weird solution, but indeed if I replace the mode B in with A in, and we can even add a phase, right? We can choose the exponential I5 phase here. So you will see that the input-output relation now, in the limit of large gain, it will become simply square root of 2g, 2 square root of g, times the quadrature x of A in, but we can again use this phase to choose which quadrature we're interested in. So it will amplify with again 2 square root of g, one quadrature, let's say x, and de-amplify by an attenuation factor 1 over 2 square root of g, the other quadrature p. Okay. So this is another solution. So this kind of phase-sensitive amplifier, since it only involves a single mode, it will not add any extra noise, right? So it will indeed this will preserve the variance, let's say, of the quadratures once referred to the input. Okay, so this and this the kind of Hamiltonian we need, the kind of unitary operation we need to make this work is a single mode squeezing. Okay, so you see we have these two devices, one that uses two mode squeezing, so which is able to generate EPR pairs on two lines at two possible frequencies, by the way, and one which is based on single mode squeezers and which implement this phase sensitive amplification. Okay. So finally, if we go back to our quantum trajectories goal, right? So we need to model the full detection setup now. So the amplification setup. So in an amplification setup, we start with some signal A naught, which comes from the quantum system, and we want to measure that. So we know that at the input we have some signal A naught. At the output, in the end, we will have the ADC, which is very noisy, and we want to amplify the vacuum fluctuations of that guy enough so that they completely overcome the 10 to the 3 photons of noise that we have at the ADC level. So what we're going to do is put a first amplifier with again G1, which is polluted by an idler B1. But usually this is not enough, right? We cannot directly put this into the ADC because typical amplifiers, they have a gain of about 20 dB. That's the standard. Going beyond is really hard. And so 20 dB is absolutely not enough to overcome the finite noise. So in the end, so we will put a chain of amplifiers. So we will put a first amplifier, then there will be a second one, a third one, and I will stop there. But you see that depending on the experiment, we may need up to 5, 6 amplifiers. So each of these amplifiers adds a bit of noise to its idler. And what I'd like to show you now is that the most important one is the first one. So if the first one does its job, usually the other ones can be a bit noisy, and we will not need these other amplifiers to have an idler mode in the vacuum to operate properly. So it relaxes a bit the conditions on the other amplifiers, which is good because typically these close to the quantum limit amplifiers that we're going to use as a first level of amplification, they will not operate on very large signals, such as the ones which are at A1 and A2. So we need to use different technologies like based on transistors to operate, and these technologies for now they're quite noisy. They do not add half a photon of noise, but more or less 5, 10 photons of noise. If it's a cryogenic amplifier. Okay, so how do we understand that the fact that how do we choose, right, these amplifiers and what noise we can tolerate? So we can compute, for instance, the variance of at the level of A1. So by this notation, I mean the sum of the two the sum of the variances of the two quadratures. So this total noise is you see G1, so that's the gain of the first amplifier, times the noise at the level of the signal, so delta A naught squared, plus this plus this idler term. So the noise of the idler is delta B1 squared. Okay. So typical notations. In typical notations, we talk about added noise, and the added noise is typically denoted as A curve A. Okay, so you see that's the noise on A1. Now, if we continue a bit this exploration, you see that on A2 we would have so on A2 we now amplify by again G2 the noise that's coming in. So if I write again this refer to the noise at the origin, so we have now again G1 G2 times the noise we want, so the vacuum noise, plus G1 minus 1 G2 A1. So that's the amplification of the added noise by the first amplifier. And now we have a new term, which is G2 minus 1 times the added noise by the second amplifier. And so you start to see how it works, right? So there's this long chain of amplification. And if I plot the final signals to noise ratio, so that's SNR is a signal to noise ratio. So let's say you want to measure some coherent amplitude, and we want to discriminate. So typical scenario I have in mind is you want to do a hypothesis testing, like measuring a qubit. So you want to determine whether the signal at the level A0 is in one state or another. And so this would correspond. So the signal would be the average value of the amplitude A naught when the system in the scenario number 0 minus the amplitude A naught when the system is in the scenario number 1. So this would be the signal at the level of the quantum system. We amplify this signal by G1, G2, G3 on the drawing, right? We have 3 amplifiers. And so that's the signal part. So note that the signal so here the signal is a number of photons, right? It's not an amplitude. I do a square of the amplitude. And at the bottom, at the denominator, we need to write the noise. So the noise would be this long series of amplified added noise. So we would have a G1 minus 1, G2, G3, A1, plus G2 minus 1, G3, A2, plus G3 minus 1, A3. Okay. So what's the condition for this signal to noise to be as good as possible? You know, so we want that. What we want is that this one, the first term here, wins is larger than all the others essentially. So the goal is so if we use indeed if we use a quantum limited amplifier, so we know that A1 is at least a half. But what we require is that it's more or less a half, right? It's not much more than a half. So we want that, and we want G1 A1. So you see A1 times the gain G1. So we assume the gain to be large, right? So G1 minus 1 is close to G1. So we want this to be much larger than G2, A2, and also that G3, A3 over G2. So if you're under this constraint, if the so what really matters is this product of the gain of the first amplifier, which I told you is typically 20 dB in the experiments, times this added noise, which is at least a half. So if this one is much larger than no, that can be right. Sorry, there's an issue here. No. There's no G2 here. Sorry, it's a G1. It's G1 A1 much larger than A2 alone. So we need to overcome the added noise at the level of the second amplifier with G1 A1. Yes. And so you see in this condition, under this condition, the total added noise by this detection setup will be limited indeed by the first amplifier. Okay. So to sum up, you see, despite the fact that amplification requires some added noise, again, because of this intrinsic noise of the ADC, we can improve the overall signal-to-noise ratio. And working on the first amplifier alone is sufficient. Okay. So finally, I'd like to define, to relate this discussion to the quantum efficiency. So the quantum efficiency is this parameter that comes in the stochastic master equation in the quantum trajectories. So eta, and so eta. So the way to define eta in this under this condition is eta is the actual SNR that we obtain over the ideal SNR. Okay, so this okay, so this is the that's the full efficiency. And so if so there are two cases, right? So if we measure if measuring both quadratures, such as in the experiment I showed with the quantum trajectories of the fluorescence, then eta is given by the variance of the Q function at the output divided by total the total gain times the variance of the Q function at the input. And here by output and input, I mean really the final amplitude, right, which I call A3, and A in would be A0. And so this can be up to 1, you see, with a phase preserving amplifier. If instead we are measuring a single quadrature, X out only, then eta will be the variance of X out divided by square root of G dot variance of X in. And this one would be at most a half if we use a phase preserving amplifier. Okay, so you see the definition of the efficiency essentially depends on what we're going to do with the stochastic master equation. So if we intend to use a single quadrature, then we'd better use a phase sensitive amplifier, otherwise the efficiency is limited to a half. But if there are two measurement records that are competing because they're coming from a heterodyne measurement, then using a phase preserving amplifier can leave the measurement, the quantum efficiency to up to 1. Okay. So finally, to give you a bit of numbers, the records. So Kater, you mentioned 90%, but I was not able to find 90%. So if you have a publication in mind, I'd be happy to hear it. But so what I found is the current record, it seems, is 80% and this was obtained in the group of Irfan Siddiqui at Berkeley. It's a paper by Edins et al. TRX 2019. And there are other papers at 70% at NIST, and another paper at the GILA in Boulder as well. Typical numbers are more in the so these are records, right? Typical numbers are more in the 20 to 40% regime. Okay, and I would say that it's a bit unfortunate because so this is still something the community needs to work on, because there are many interesting effects in quantum trajectories that would develop if we were able to reach 90, right? 90% would be, I think, a good, would be a bit of a game changer if we want to see a very interesting effects. But yeah, so here we are with the current numbers. Okay, so that's what I wanted to say about amplifiers. Do you have question on this part? Or yes? So that's a very interesting point. Indeed, these amplifiers, they when they operate, we can define what's called the 1 dB compression point, which is the power, the input power of the signal at which the gain drops by 1 dB. And indeed, this so depending on the amplifiers, it can be coming from two origins. The first one, which often happens in quantum optics, is called the pump depletion. It's the fact that typically these amplifiers, they work by sending a pump at some frequency, and the photons of the signal that's coming in, they would essentially multiply by breaking the pump photons into pairs, or it can be various situations. But if you input a signal with a too high power, then at some point it's possible that the pump does not provide enough photons per second for you to generate enough gain. So that's pump depletion. In superconducting circuits, these circuits are usually very nonlinear compared to their optical counterparts. And so what happens more usually is the fact that as the signal rises, as you increase more and more the signal, the frequencies, the resonant frequencies of the modes that constitute the amplifiers, they shift. So if you want, the nonlinear means that the frequency depends on power, right? And at some point, what happens is that they shift so much that the resonance condition between the pump and the signals is not matched anymore, and so the gain drops. So these are. Yes, I mean there are trade-offs indeed like this, but then you would have to fight against pump depletion. But indeed, this is that's a trade-off. Yes. There was another question. Well, so that's that's a tough one. Yes, so in some amplifiers, the efficiency is so, for instance, in these traveling wave amplifiers, the efficiency is limited by two things. One is the intrinsic losses of the materials. So in this kind of amplifiers, there are dielectrics that contain two-level systems that may resonate with a signal, and this introduces losses on the way. Another problem is the fact that the signals along their travel may not be phase matched properly in the end, and so this induces reflections, internal reflections, and diminishes the efficiency. And then yeah, I'm not sure there's a general answer to your question. On paper, we should be able to bring this up to 99% at the level of the amplifier itself, right? There's no intrinsic limit, I would say. But of course, then we would need to fight against the other amplifiers need to be good as well, right? If the first one is that good, if we're so close to 100%, then the next amplifier then would need to be a bit less noisy, maybe than the one we have. So this 80%, it was obtained with an amplifier which was really close to the system of interest, and which was followed by a traveling wave amplifier, so another quantum limited amplifier. Yeah. Okay. So maybe let's maybe continue with the slides now. So okay. So yes. So we in the previous talks we discussed already these all these points. So I'd like to show you an experiment that realized the entanglement by measurement now. So it's a quantum trajectory of 2 qubits that are measured simultaneously, and the measurement provides some entanglement between the systems. So this experiment was done in a few groups. I mean 2 groups actually. So the group of Leo Di Carlo and the group of Irfan Siddiqui. And so here, so the slides are coming from Nicolas Roch, who was postdoc at the time in Berkeley. So here is the setup, right? So we have two circuit QED setups. So we have two transmons and their cavities, and they're arranged in such a way that we can send in a signal which would probe the first transmon, and then propagate towards the other cavity, and finally go out and be measured. So if we send the signal, a signal at the input at the frequency of the 2 cavities, so the 2 cavities are on resonance, then the signal at the input would look like the Wiener function would look like a lollipop like this, right? And at the output of the first cavity, you know that these lollipops will be phase shifted up or down depending on the quantum state of the transmon. So this would be so that's the standard dispersive readout we already discussed. But now when the signal arrives at the second one, if the phase shift is the same for the second qubit than from the first, you see that there are 4 possibilities now. So if 2 qubits are in 1-1, the 2 phase shifts add each other, and the lollipop gets very high. If the 2 qubits are in the 0 state, the 2 phase shifts add each other, but they go very low. But on the other, in the 2 other cases of 1-0 or 0-1, you see that the 2 phase shifts actually compensate if it's idly done, and so they compensate in such a way that these two measurement outcomes, the measurement outcomes corresponding to these 2 possible quantum states of the bipartite system, they're the same. So essentially, if we measure, so here there's a quantity that we can measure, which is the integral of the voltage along this quadrature, which they call little r. So if you plot a histogram of the values of little r as a function of the qubit states, you see that indeed there's almost a perfect overlap between the measurement outcomes corresponding to 1-0 or 0-1. And because of that, it's possible on paper to prepare an entangled state by measurement. So, namely, if we detect a value of r which is around here, there's no way of knowing whether the system is in 1-0 or 0-1. So what the protocol to prepare this entanglement is therefore to start with a separable states. So this quantum state is not entangled. It can be prepared by doing a pi/2 pulse on each of the 2 qubits, and then we will measure the 2 systems. And if we arrive at the middle, the only thing we can say is that the qubits are not in 0, 0, neither in 1, 1. And so the system will be projected on the only remaining possible submanifold, which is 0, 1, 1, 0. So it will prepare a Bell state. So and so you see if you do that with a projective measurement, indeed, and reconstruct the density matrix of the bipartite system, they indeed see kind of a Bell state with some infidelity, of course, but the concurrence, which is a measure of entanglement for these 2 qubits, is positive, right? So it means that indeed these 2 systems are entangled. And now they went a bit further. So they looked at a quantum trajectory approach of this entanglement, and they were able to see as the time evolves how the entanglement builds up between the two systems. And for that, they use a Bayes rule to map this parameter, so the integral of the voltage, the integral of the quadrature they measure as a function of time, and they can map this R parameter to the density matrix. So it's, if you want, it's kind of a stochastic master equation, but here it's written as a Bayes rule. So if they look at a single trace, so now so before these were average measurements with tomography. Now I show you a single trace of their measurement. So they see something quite noisy like this. So here these 2 colors. So the 0 value would indicate that the system is in 0, 1 or 1, 0. Blue would indicate 0, 0, and red 1, 1. You see that the noise is larger than all of this, right? But despite that, if you look at this single trajectory and measure R as a function of time, so this parameter R, which is again the integral of the quadrature as a function of time, so you see that R evolves like this, and if they reconstruct the quantum trajectory of this bipartite system, they see this evolution where at first, it's both, so the probability actually to be in 1, 1 is the larger. But then at some point, 1, 1 and 0, 0 gets really low. And the only remaining terms are these 2 diagonal terms for 1, 0 and 0, 1, and the cross of diagonal terms corresponding to 0, 1, 1, 0, which reveal the quantum correlations between the two qubits. And so to be more quantitative, they plotted from this measurement of the density matrix in time, they plotted the concurrence, which is again a measure of entanglement here, the concurrence as a function of time, and they can see on a single realization of the experiment, on a single trajectory, they can see the concurrence building up. So this is this was a very nice experiment. Okay, now a different topic I'd like to show you. So we discussed up to now quantum trajectories of qubits. I'd like to show you that we can also reverse the perspective and use qubits to measure the trajectory of a cavity. So the trajectory of photon numbers. So this was done in the past by, for instance, with the Rydberg atoms in cavities by the Roche group. Here I'm going to show you a different technique. So first, let me remind you what's the traditional way of doing this, like the Roche way, let's say. So the system is the following: we have a microwave mode which contains a given number of photons, and or even a superposition of them, and we want to measure using a qubit how many photons there are. So the traditional way is to encode some binary information about the photon number in the qubit, and then read out the qubit. So here, for instance, what we could do is use the dispersive Hamiltonian, which says that the qubit frequency depends on the number of photons in the resonator. Okay, and what we can do is send a wave packet, a pi pulse, at the frequency of the qubit, at the frequency that the qubit should have if there are 0 photons in the resonator. So we send this pulse, and we check whether the qubit is excited or not by doing a readout. And here, if the cavity contains 2 photons, you see that the answer will be no. The qubit is in the ground state because this pi pulse at that frequency is not resonant with the qubit, so it could not excite it. And we repeat the experiment, right? We continue in the same run of the experiment. We now send a pi pulse at the frequency of that the qubit should have if there was 1 photon in the resonator. Again, the answer is no. We send one at the frequency fq minus 2 chi that the qubit should have if there are 2 photons. And this time we see the qubit is excited, so yes, we know that there are 2 photons. So this strategy of measuring the number of photons, you see it's quite, well, it's sequential. We need to adapt the question we are encoding, the binary information we're encoding at each time step. We are adapting it at each time. We're changing the question at each time. And there are optimal ways to do it. I showed you a way which is the binary decimation last time. There are other ways, right? But each time we need to apply the different unitary operations to the qubit or the readout in order to encode one question out of a time, one question at a time. So I'm going to show you now another possibility, which is to instead of using the qubit as a pointer, we are going to use the qubit as an encoder. And the difference is the following. So instead of sending these pulses one by one, we're going to send all of them at the same time. And the qubit will not be, so this time the qubit will not encode some binary information about the cavity state, but its reflection properties, if you want, the fact that it will modify these all incoming modes into a different state depending on the number of photons in the resonator. So if there are 2 photons, the wave at that frequency will be affected, and we will be able to measure that if we build a detector that is sensitive to each of these modes. So this is the principle of frequency division. So instead of doing one at a time, we simply send all these drives and measure continuously what's coming out, and infer after a certain period of time. We would build a quantum trajectory of the cavity state and infer what is inside, right? Okay. So all right. So maybe to give you some analogy, we're going to say that the number of photons in this cavity is a number of apples in the basket, and I'm going to show you how we can do this. How we can do this frequency comb. You know that the frequency comb in the time domain is a series of kicks, right? It's the Fourier transform of a Dirac comb is also a Dirac comb. So what we're going to do now is the analogy I'm going to propose to you is this bag of apples. So let's say here there are 4 photons, so 4 apples. And in order to count the number of apples, I'm not going to simply look at them. I'm going to attach this bag of apples to a string with a levy here, and the string will play the role of the qubit. And what we're going to do is hit the string with a hammer in order to hear what's the sound it emits. And depending on the number of apples, you know that the stress on the wire will differ, and so the sound will be a bit different. So the principle of the experiment is really this one. We're going to hit with the hammer repeatedly on the string and simply listen to the frequency of the wire. And when an apple will be kicked out of the basket, we will see a change in the frequency that we hear. Okay, so this is the principle of the experiment here. So again, the qubit is the wire, and the heterodyne measurement we are performing will be equivalent to this microphone. Okay. So all right. So what we do in the experiment, so we kick the qubit repeatedly like this, and we do it. The pulses are so fast that the qubit is excited well over the number of photons in the resonator. And if I plot here what's the trajectory of the qubit in its Bloch sphere after a kick, so you see that repeatedly what happens is that the qubit is kicked. For instance, we can choose, right, the amplitude of these kicks in order to choose the angle of rotation, and so we can end up here, for instance, on the equator of the Bloch sphere, and then then we wait. The qubit will decay, and it will decay spiraling at a frequency that reveals the number of photons in the resonator. So the typical trajectory, if we measure sigma x, which sigma x, I remind you that it's one of the two quadratures of the spontaneous emission by the qubit when we record it in a heterodyne way. So a typical trajectory of sigma x would be a kick and then a decaying oscillation like this. So that's for 0 photons in the resonator. If we have instead, let's say, a different number of photons, I think it's 1 here, so you see it will what's going to change. So there will be the same kick at every time step, but now the frequency of these oscillations will change. Okay. So this is the principle of the experiment. So indeed, we need, in order to get a large signal strength, a large measurement rate, we need that the qubit is very short-lived in order to release these excitations as fast as possible. Okay. So the measurement setup will be the following: where we have a qubit connected to a cavity. We're going to drive the qubit directly with these fast pulses, and measure with a traveling wave amplifier. We're going to measure what's coming out. So what's coming out is composed of a few terms. One is simply the reflected pulses that we send in. The second one will be the signal. It will be it's really like 2 days ago, right? We are going to record the fluorescence emission and hence record the sigma x component of the qubit trajectory. The efficiency of this traveling wave amplifier and the whole system efficiency is 17% here. So you see well below 80. And finally, we would have this the quantum noise, right? This Langevin term here, or it's a Wiener process that we had at the end. Okay. So we did the first experiment in 2021, where it was in 2D like this. So the cavity was this coplanar waveguide resonator. The qubit was in red here, and the qubit decay time was 42 nanoseconds. But the storage time, the lifetime of the cavity was only 4 microseconds. So in fact, it was not long enough for us to demonstrate any quantum trajectories. We could only show a proof of principle that on average it can count the number of photons. And so in order to really see trajectories, we needed to keep the qubit coupling rate that low, but extending quite a bit the decay time of the resonator. So what we did is went to 3D, where the lifetimes are longer. So this is that's the new experiment. So we have a 3D aluminum cavity. The qubit is here, and then there's some important point is that we want the cavity to be well decoupled from the environment, but we want the qubit to be strongly coupled both to the cavity and to the environment. So you see that's a bit counterintuitive, because that would provide a decay channel from the cavity to the outside world. So what we did is engineer a filter that provides a notch at the cavity frequency, so that the cavity photons cannot exit through that line. Okay, so in practice it looks like this. So we, well, there were a few innovations, but maybe it's a theory audience. You won't be sensitive to this. Let's move on. So all right, so this is a typical signal of the qubit. So that's the, so here we measure the average signal of the qubit when we prepare 0 photons, so the vacuum in the cavity. So here I average the signal 60,000 times on 60,000 realizations. And maybe to better understand, I'm going to convert light at 6 gigahertz to a sound at 440 hertz that we can hear. And so we can now hear this experimental signal with our ears and not our eyes. This is what it looks like. All right. So now, if we add 1 photon in the resonator instead, this is the average signal we measure. So with the eye, we barely see that the frequencies are a bit different, you see. Let's see if we can distinguish them with our ears. So that's only 400 millihertz of difference. See the difference, right? And one way to see that they are different is to play both at the same time. And in this case, we should hear some beating between the two. So let's hear that. See, they are different. So the goal of the experiment is to distinguish them. We have one signal like this for each number of photons. So with 4 photons, it's a bit more different. The frequency is a bit further away. If I play at the same time, the beating is more pronounced. The beating is now larger. Okay. So what does the quantum trajectory? Building a quantum trajectory means here, right? So instead of these average signals, we're going to work on a single realization of the experiment. And the signal, unfortunately, is very noisy, right? A single realization of the experiment, we barely see only the quantum noise. So if we so the goal of the experiment is to make sense out of what you just heard. So what you heard is some noise on top of the interesting signal. So we need to start from this very noisy signal and infer which one of these signals is hidden below the noise, right? And so this is what we do. So the way to do it is to take these experimental averaged quantities and demodulate so we will demodulate this very noisy signal with the average of these signals in order to get manageable data. And it turns out that doing this does not remove much of the information. And maybe okay. So what we're going to do is we want the probability. So very quickly you will see that we end up in the diagonal of the density matrix. So we're going to focus on the diagonal and just plot compute the probability to have n photons at a given time, and we're going to use a Bayesian update for that. Okay. So how does it work? So the experiment starts like this. We send a displacement. So we prepare a coherent state in the resonator, and then we kick this qubit with a frequency comb. And here is one example of such a number photon tracking. So here in color, you see the probability that we compute from these trajectories, the probability from these measurement records, sorry. We see the probability to have a given number of photons at every time step. So you see that at the beginning for this one, we have 7 photons. And then we see quantum jumps where we go to 6, 5, etc. Right? And you see that so there was no quantum smoothing here. We just plot the forward trajectory. So we see these quantum jumps. If we plot a different, we do a second measurement, so we will get a different trajectory, of course, and etc. Right? So you see, we can with this indeed now build proper quantum trajectories. And again, what's different compared to what's been done before is that we don't need to change the question each time. We don't need to change the unitary operation at each time step. We just turn this on and measure. Okay, so here are a few trajectories. So to characterize the quality of this measurement, or maybe how well we extract information, it's actually a good question to wonder what's the measurement rate at which we acquire this information on the number of photons. But also we can wonder what's the maximal rate we should be able to reach. And it's a bit of a different question that so Klaus mentioned this. It's there's also the not early. Okay, sorry. Okay, I'll be fast. So there's also the dephasing rate, which tells you what's the maximal information what's the information that goes out in the environment. Okay, so to compute the measurement rate, we compute the mutual information between the signal and the distribution of photon numbers, and the measurement rate is this mutual information divided by the time, and if we plot this, so that's the measurement rate as a function of the angle of the first kick of each kick in the Bloch sphere. So interestingly, you see that there's almost no measurement rate near pi, and the reason is that with this heterodyne measurement record, we're measuring sigma x, and you see that if we do a pi pulse, if we kick towards the North Pole, the trajectory will go straight down, and so sigma x stays 0. So there's no information to recover here a priori. Whereas if we kick on the equator, sigma x is maximal, and so we get the maximal amount of measurement rate. We can compare this measurement rate here, which is 1 per 13 microseconds, to the storage time, the lifetime of the resonator, which is much longer, and this is why we were able to do these trajectories. Okay, so we can do the simulation and reproduce quite well this measurement rate here. Now, if we want to compute the dephasing rate, we can actually measure the dephasing rate. So this seems counterintuitive, but we can know what would be the maximal rate at which we could recover information. In a sense, if we were the environment, what could we get from this from what's coming out in the environment? So to do it, we do a tomography of the cavity state. So here I'm plotting Wigner functions, the ones I defined in the lectures. So Wigner function of the vacuum, Wigner function of a coherent state, a Wigner function of the Fock state. So this is what Wigner functions look like. They have negative parts. Okay, so this is just the theoretical expression of the Wigner function. But with the experiment, we actually have a second qubit that we can use to measure the parity of the cavity state, and hence to measure Wigner functions, and we can actually prepare all these functions, right? So this is the result of a direct measurement of the Wigner function when we prepared all these states by heralding on the result of our photocounter. Okay, and so to compute the dephasing rate of the cavity under our measurement, what we do is we start from a coherent state, and we watch how this coherent state evolves in time. And after some time, you see what happens is that the coherent state has rotated, but also it gets blurred, it gets spread in phase. And this spreading in phase is precisely due to the dephasing induced by the measurement. So by computing now how fast it spreads around the circle like this, we can compute the so this is that's if you want a measurement of the amplitude, right? Which gives us a measurement of the coherence. So we compute the dephasing rate like this, and this is what we get. These are the blue points are the experiment, and interestingly, there's now the dephasing rate is maximal at pi. So it's maximal when we excite the qubit. That's also when there are there's the most energy to get out of the qubit. So that's when the most information has to be provided to the environment. But it's also where we measure it the worst. Okay, so the model is so-so. It works well at 2 pi, and after we don't know why it doesn't work. That's the measurement rate in the experiment. You see, much below, owing let's say there's about a 15 factor. Factor of 5 comes from the inefficiency of the detector, and the factor of 3 comes from something interesting, which is the fact that the heterodyne measurement gets only about a third of the full signal, even if we had perfect efficiency. But maybe I won't. I will not explain this. And okay, so I will stop here. I just want to thank the people who did all these experiments I showed you, right? So the experiments I showed were taken over many years actually. So this is a picture of the group. So the group now is down here, and so here I'd like to thank all of them for contributing, especially Hector Hutin, who helped a lot for the lectures of part 2. Okay, and I thank you for your attention.
Very much for this beautiful and very rich talk. Do we have any questions from the audience? Maybe we can take 1 or 2 before going to break.
Thanks, Benjamin. Can you explain why the heterodyne detection only picks up a third of the signal, or whatever you say?
Yeah, so this is so that's thanks for the question. It's very interesting. So yeah, so we were puzzled by this, right? So the maybe I can show. So all right. So first the heterodyne detection. So first thing that's surprising maybe at first is that indeed even at pi now we have a maximum. So the heterodyne detector we believe that it measures sigma x, and so sigma x is 0, so we should not be able to get any information out of this. But in fact, what's happening is that so if we have a very good efficiency, it's possible to distinguish a case where the qubit is excited and releases a fog state from a vacuum state. So if you want, the heterodyne detection can detect that there's more noise. Yes, the second moment contains information. And so the way we compute this is by looking at the UZMQ functions of the two possible, the several possible outcomes. And indeed, you can show that the heterodyne detector is imperfect. And if I will try to be fast, but so if we compare the information, the mutual information that we acquire, so let's focus on the situation where we are, where the lifetime of the measurement is longer than the measurement, than the difference between the frequencies of the qubit, corresponding to each number of photons. So you see that indeed if we compare the accessible information as a function of the excitation of the qubit to the heterodyne information you can get, you get this factor of a third. If we were to measure with photodetectors, we could get all the information at when the qubit is fully excited. But this a third depends on you see, it depends on how resolved the detector is. So if two photon numbers are overlapping a lot, we're in this configuration, in which case the heterodyne is better than the photodetectors. So it's a rich rich parameter space. Yes.
Is there any questions? Yeah.
Thanks. My question is about that when you send a lot of photons at different frequencies to probe the cavity, because there are a lot of photons, does it mean that you also get in single shot like full statistics of the cavity, or do you have to do many measurements to do the statistics if you want to do?
Yes, so it's a single shot in the sense that before the cavity decays, we get the answer, right? We get the number of photons indeed before. But indeed, it's we don't get that information. We don't get in a single kick. We need to measure for some time, and which I think is about I think it was about 20 microseconds for a fidelity of 90% or something.
Okay.
Yes.
Thanks.
So if there's no other pressing question, I suggest that we continue like on the break, and we could reconvene at 11:30, right? So let's thank the speaker again for this wonderful.